Hello guys and gals. In this video, we're going to be focused on the second part of 5.3. So when we ended off last time, we'd just gotten done talking about these things. Integrated rate law relates to concentration and time, or it relates concentration and time. There are three different ways to write the integrated rate law depending upon the order of your reaction. The order of the reaction can be determined by drawing three graphs: concentration versus time, natural log of concentration versus time, and the reciprocal of concentration versus time. Whichever of those graphs is most linear will tell you what the order of your reaction is, and therefore which integrated rate law to use. From there, K can be solved for by finding the absolute value of the slope of your graph. You could also be asked to solve for concentration, time, or regular rate law using the integrated rate law. One other thing that I want to make sure that we review here, since I covered it so quickly on the last part, is that on the AP formula sheet, you will not be given them in the y equals mx plus b format. These are the only two that you'll be given, so you won't even be given the equation for zero order. So we definitely need to know that one, which is exactly these two, just regular concentration, okay? But this is the way that you'll be given those. Now, it is the same thing as y equals mx plus b. The only difference is that it just has been rearranged algebraically. So we'll work with this from now on when we use these, okay? So all we're going to do now are some sample problems, okay? These are sample problems that I took from some other AP notes, so they are not AP practice problems. These are just sample problems to help us become more familiar with integrated rate law, okay? So this says the decomposition of N2O5 was studied at a constant temperature, and they've given us this table with information in it. Notice this is concentration versus time. So this is going to tell us immediately that we are going to need to work with integrated rate law. So let's find out what the question's asking. Determine the rate law and calculate the value of K. Now, this is very important. They do not say determine the integrated rate law. They want regular rate law, okay? If they wanted integrated, they would say determine the integrated rate law, but they don't. They want regular rate law. But the problem is we're not given regular rate law information. We're given integrated rate law information. So what exactly are we supposed to do with that? Well, let's think about it. In order to solve for regular rate law, the only thing that I have to know is the order of my reactants. Well, in this case, I only have one reactant, which makes my life nice and easy. It's N2O5. So can I use integrated rate law data to solve for the order of my reactant? Yes, I can. And then if I solve for the order of my reactant, I can solve for regular rate law. So let's do that first. Let's solve for the order of N2O5. So I've already put the graphs on here for you. This is just concentration versus time. Notice that this graph is pretty exponential. It is not linear, so this is not going to be a zero order reactant. So let's move on to first order. This is natural log versus time. That means that if this graph is linear, our reactant is first order, and it is. It's very linear. So this means that the reactant is first order. If you want, you can go through and you can do the reciprocal versus time graph just to make sure, but you're timed on the AP exam. So if you get something that's this nice like that, I would suggest going with first order. You can always go back to it and double check if you have time, okay? So the reactant is first order. Well, since we know that the reactant is first order, we can write the regular rate law, because regular rate law does not require us to solve for K to write it. It just is rate is equal to K times into the concentration of N2O5 to the first. And that's our order, or that's our answer for our first one. Again, it did not say solve for integrated rate law, but we had to use integrated rate law information to solve for regular rate law. So pay close attention to the question that they're asking you, okay? Now the second part of this question asks you to solve for K. There are two ways that we could solve for K in this equation. We could use the integrated rate law for first order and choose any point on the graph and go with it. Or we could find the absolute value of our slope in our natural log versus concentration, or natural log of concentration versus time graph. Either way is fine. Both of them are going to give you the same value of K. I'm going to use the integrated rate law way to show you this. Plus, if you don't have a graphing calculator, this way is going to be easier for you to solve for K. So this is the formula that you're given on the AP formula sheet for a first order integrated rate law problem. So I'm just going to pick any data points that they've given me from the table or from the graph. It doesn't matter. Now, they've given us the table, so I'm going to use that because it's a little more accurate. And I picked when my time was 400 seconds, and this makes my natural log of my concentration at that time negative 5.07, okay? The natural log of my initial concentration is negative 2.3. So all I did was I went to the table, I chose a point on the graph that was not my initial point, right? I chose a point on the graph that wasn't my initial point, and I inserted it into this equation. So we substituted information in here. And then algebraically, I can solve for K. Your K value should never be negative, right? So please keep in mind that if you solve for K this way, divide something by -1 along the way because your K value is not negative. It cannot be negative. So there we go. If you wanted to solve it for slope the way I mentioned above, you could always do this, which I did the exact same thing. Notice that I used the natural log of concentration data for my y-axis. I did not use regular concentration data because this is a first order reactant. I have to use natural log of concentration every time I want to solve for something that deals with integrated rate law. Okay, well, that deals with a first order integrated rate law, and in this case it does. So we've got to have positive K, so if you solve it this way, please make sure that you include absolute value signs. Okay, so the final answers we've solved for our rate law and for our K value. Notice the unit on this, because it's first order, our unit is time to the -1, or 1 over time, right? So that is A. For B, determine the concentration of N2O5 at 250 seconds. Does our calculated answer make sense and justify it? Well, now that we have the K value, we can solve for pretty much anything. We could solve for rate at a specific concentration. We could solve for concentration at a specific time, or we could solve for a time of a specific concentration. In this case, they're asking us to solve for concentration at a specific time. So because they've given us a time value, we have to use the integrated rate law. There is no time value in regular rate law, so we cannot use that to solve this problem. So again, all I did was I took this from our AP formula sheet and I substituted the numbers in that they had given me. I solved for K, so this is my K value. Now notice in the equation, I do put the negative in front of it. That's not saying that K is negative. Really, it's more like -1 times K. That's only there to account for the fact that the slope is negative, okay? I put in my natural log of my initial concentration again, and I multiplied it by the time that they've given me, 250 seconds. And then I can just solve for this algebraically. Keep in mind that the opposite of natural log is e raised to the power. So in order to get rid of that natural log, I raised both sides to e, or I took both sides and I raised e to them, okay? So I finally end up with x is equal to 0.0177 molar from this problem. Now, that's not all that you need to do for this question. They're asking you, does your answer make sense, and justify that. So let's talk about it. They wanted the concentration of 250 seconds, not the natural log of concentration. So I had to solve algebraically for the regular concentration, not the natural log. The problem is that our original data did not include 250 seconds. So it did include data at 200 and 300 seconds. Well, since 250 is between 200 and 300 seconds, then our concentration should have been between these two concentrations that were at those times. So is our answer in between these two original concentrations? And the answer is yes. So this question does make sense logically. All right, I'm going to call it here for this video. I hope that this helped, and let me know if you have any questions. Maybe.